Welcome everyone to the fourth and final session in our series, Understanding and Exploring Network Epidemiology in the Time of Coronavirus. We've had a great series so far. I want to thank our speakers in the first three sessions, and I'm very confident we're going to have a great seminar today from Ginestra Bianconi. But before I introduce her, let me give you a few more details. First, I should say I'm Michelle Gervin, professor of physics at the University of Maryland, and I'm director of the Combine program in network biology. Combine is one of the sponsors of this series in partnership with the Vermont Complex Systems Center. So, as I've mentioned, we've had some great talks in this series so far. If you missed any of them, please go to our event website, go.umd.edu/netcovid, all lowercase, all one word, for links and to videos from other sessions and for other materials. We also invite you to follow us on Twitter, #net_COVID, or you can follow Juniper Lovato, who is one of the co-organizers and the program director at the Vermont Complex Systems Center, or you can follow me at Gervin Michelle. In this session, as in the past, we really encourage you to ask and answer questions in the chat window. And then also, we invite you to join the parallel sessions, which will follow the seminar today. So if you go to our website, you can get a detailed schedule and the Zoom links for those individual sessions, but it'll start off in this same Zoom meeting session that we're in right now. And also, so one thing that has made this seminar series and workshop series so great are all the participants we've had from various diverse backgrounds, and we've wanted to reach all of you, and we thank you for participating. So if you could give us a little feedback, we invite you to fill out a short survey for us. So if you signed up to receive information about this series by email, you'll receive a link to the survey by email shortly, and any feedback that you have is greatly appreciated. So that's all for the logistics for today. Let me turn now to introduce our speaker, Ginestra Bianconi. We're so excited to have her today. She is a professor of applied mathematics at Queen Mary University of London. Ginestra did her PhD at Notre Dame University, and before she went to Queen Mary University, she was an assistant professor in physics at Northeastern University in Boston. She is also currently an Alan Turing Fellow at the Alan Turing Institute. Ginestra is really well known for her foundational work on the mathematics of complex networks. She's worked on a lot of different types of problems, work on, early work on degree distributions to work on multi-layer networks, and more recently she's been applying this mathematical modeling to thinking about epidemic spreading, and in particular thinking about the containment measures that are necessary to tackle the global pandemic that we're now in. So with that, I'd like to turn it over to Ginestra, and I look forward to an exciting presentation.
Hello, everybody. So let me share my screen. Here we are. So I would very much like to thank Michelle and Juniper for the incredible energy for organizing this very timely seminar series and coordinating this wonderful project. And I really enjoy all the talk that preceded mine. So thank you so much, Lauren, YY, and Sam for the wonderful presentation. So as Michelle has said, I'm professor in applied mathematics at Queen Mary University of London and fellow of the Alan Turing Institute. And I've been working on networks for about 20 years. And in this talk, I would like to provide an overview for the challenge of the current COVID pandemic is posing for mathematical modeling of epidemic spreading. And I will touch both these challenges at the level of well-mixed population and at the network level. And in particular, since recently I've been working on multi-layer networks, simplicial complexes, and temporal network, I will like to highlight the effects that this generalized network structure have on epidemic spreading. So after more than 1 month from the date at which the WHO has declared the COVID pandemics, worldwide, the population is getting used to the sad, deadly update on the number of cases and the death toll of the epidemics. And some of us have also personal experience related to this pandemic. So despite the true numbers may be far from the official numbers, these official updates provide a grim picture of the global spread of the disease. So it is natural that the scientific community is reacting strongly by using different expertise to understand the spreading of the disease, to trying to inform government policy and trying to predict the future and the dynamics of this disease. So where does epidemic modeling has its origin? So we can trace back the origin of mathematical modeling of epidemic spreading to the 18th century, exactly in 1760, when Daniel Bernoulli wrote an important paper to promote vaccination procedure in mitigating the smallpox pandemics and made the case for the widespread diffusion of this vaccination procedure against, guess what, the no-vax movement of that time. And I believe that a quote of Daniel Bernoulli is particularly relevant in this current situation. He wrote, "I simply wish that in a matter which so closely concerns the well-being of the human race, no decision should be made without all the knowledge which a little analysis and calculation can provide." And so in this talk, I would like to provide an overview of the current status of what Daniel Bernoulli would call a little analysis and calculation, which is actually a collective knowledge that we have gained with the help of modern epidemiology theory and network science. Of course, my account will be partial. I will reflect my specific point of view. So I'm already sorry if I miss some to cite very relevant papers on the topic that escape my radar. So in this talk, I will first discuss the challenges that the COVID-19 pandemic is posing for the network scientists. And then I will provide a minimal background for well-mixed population. Although this subject has been covered by previous talk, I think it's necessary to understand the epidemics and to keep this presentation self-contained. Then I will speak about a recent work with Paul Krapinski on modeling containment measure. And finally, I will discuss the effect of epidemic spreading beyond the important effect of the degree that has been already discussed in precedent talks. So let's start by the question many of us are asking to themselves and to their collaborator. Which model to choose to model COVID-19, where there is community spreading and limited track and testing, so limited knowledge about the real networks beyond this spread. So of course, commuting patterns and worldwide airport networks are key for the global diffusion. At the local scale of a city, for instance, the airborne disease like COVID-19 is favored by contact due to proximity, so public transport, social activity, workplaces, healthcare. So these virus prefer proximity rather than just the contact, which are studied by network scientists, which characterize more social science than just proximity. Maybe an exception, a relevant exception, is the case of the face-to-face interaction network studied in great detail, but in confined environment, a conference, an hospital, by the Socio-Pattern project. So if we go back to our question, an answer is, an appropriate model for modeling these pandemics is a metapopulation model, where at the level of a city, at the local level, we consider a well-mixed population approach, or an approach in which we have a compartmental models where the population is described just by classes of age groups. And the network is remains just a network of commuting patterns between different cities that link this well-mixed population. So at the local level, we are reduced to the well-known, well-mixed population where each individual is equally likely to interact with any other. And in this scenario, the data are constituted essentially by exponential and different exponential, one for each countries. And this corroborates the need to understand the epidemic spreading at this very general level. So people are working on this exponential, they are fitting this exponential, and they are looking at more and more exponential, and this has left the space for some humor. However, I believe that there is an important reason why exponential attract the interest of the scientists. One, first of all, is that they are a wonderful verification of epidemic model, maybe trivial, but for a quantitative scientist to see this confirmation of a theory is always worth noticing. Secondly, exponential difficult to grasp by the general public, and this explains the delay response of many governments. But if we just focus on some positive example, the fact that the German Chancellor Angela Merkel has deemed necessary to speak about the difference between R not equal to 1 and just R not equal to 1.1 leading to exponential growth, or 1.2 or 1.3 is a clear evidence that the public needs to be warned about this situation, the impact of this exponential and the thin ice and this critical situation in which we are. So exponential are important, but actually they're indication that there are also other relevant functions. And indeed, a recent work by Ziv and Ziv has shown that the WHO data on China death can be fitted by a power law, which fortunately lasts less than 2 decades. So the question is this result justifiable theoretical, or do we need to worry about the quality of the data as always in these days? And we will be back and trying to answer this question. Actually, the scientific hype of this exponential is almost fading away, as in some countries we start to see the positive effect of containment dynamics. So the death data seems to have a peak, and however the data seems to fall down, to decrease after the peak very, very slowly. And this and for this reason, people have started to call, instead of this phenomenon, instead of a peak, a plateau. And so there are different questions that one can ask. So first and originally, the question everybody was asking is, how can we flatten the curve? And for this question, there appeared to be a consensus that containment measures are effective. And this is why most of the country have taken this measure. The second one is more theoretical one, is what is the mechanism according to which containment measures suppress the epidemics? And third is how to predict the length of this plateau. If we reach this peak, how to predict how long should we wait to see the extinction of the disease. So let me start with a simple model, maybe an oversimplified model, the SI model, in which you have two compartments of individual, the susceptible individual and the infected individual. And the model is very simple. There is just one process. Every susceptible individual, if he's in contact with an infected individual, then he will become infected with rate lambda. And we can study this model in a simple deterministic approach by considering the fraction of susceptible node and the fraction of infected node. And this equation is nonlinear, but at the onset of the epidemics, we can assume that most of the people are susceptible, and therefore we can linearize the equation, leading to a simple exponential growth, which says that the fraction of infected individual increase in time exponentially for any infectivity lambda. Of course, there is a more realistic model, the SIR model, in which there are, instead of two compartments, there are three compartments: susceptible individual, infected individual, and removed individual. So the model consists of two transitions. So the one that we discussed earlier in the context of the SI model, in which a susceptible individual becomes infected at rate beta if he's in contact with an infected individual, and another process which describes the removal of infected individual from the population, which is an infected individual becomes removed at rate mu, and this removal can indicate immunization, or sadly can indicate death. So of course, the easiest approach for understanding this model is the deterministic approach. So we are now working with three variables: the fraction of susceptible individual, infected individual, and removed individual. And after taking the infectivity to be the ratio between beta and mu, we can write directly the equation for the rate at which the susceptible and affected individual change in time. By linearizing this equation and get at the onset of the epidemic, so when the susceptible individual are the vast majority of the population, then we get an exponential growth of the fraction of infected individual. But if we look closely, we get a growth only if lambda is greater than 1. So this defines three regions: a supercritical region for lambda greater than 1, in which the fraction of infected individual increases exponentially; a subcritical region in which lambda is less than lambda c and this individual decreases exponentially; and a critical phase in which lambda is equal to lambda c is equal to 1. So this deterministic model predicts constant fraction of infected individual, but effectively we know that the stochastic effect would lead to extinction of the disease. So the epidemics has this phase transition. So we have, and this depends on R0, which is the reproduction number, indicating the number of secondary infection due to a single infected individual. And R0 for this model is just equal to lambda. So we have a transition for R0 equal to 1. And if R0 or lambda is greater than 1, we have an epidemic outbreak. So a finite fraction rho of the population is affected by the epidemics. If lambda is less than 1, we have an absorbing state. And at the critical point, the epidemics is critical, so it doesn't span a finite fraction of the epidemic of the population, but it still affect a very large number, a number that increases with the population size of individual. So let me now discuss with you one work we recently written together with Paul Krapinski, which aim to address the question: which is the mechanism by which containment measures affect epidemic spreading? As a network scientist, the first answer is that with containment measure, the network change, and this is indeed a very relevant effect of containment measure. But here we address the question of timely detection of the cases. So since the beginning of the pandemics, the WHO has recommended timely identification of the cases with isolation, testing, and tracing. Moreover, a recent science paper by Ferretti et al. Highlighted the benefit that digital contact traces can have in detecting timely the positive cases, and in particular, isolating asymptomatic individuals soon. So, digital tracing has been suggested for removing the advantage that this virus has engineered to become so pervasive with its asymptomatic onset. Therefore, time is really important, and containment measures, whatever they are, they must be fast. We build a very simple model of epidemic spreading in presence of containment measure. In this model, we assume that the infectivity lambda of an infected individual in presence of this containment measure is stressed or modulated by a decreasing function tau, where tau, f of tau, where tau is the time elapsed since the infection of the infected individual. Therefore, f of tau describes the possible interventions such as self-isolation or test tracking. So with the dynamics is very easy. We start with a single infected individual, and at each time, every individual infected time t minus tau infect an average number of individuals given by lambda. So for the constant kernel, we recover the SI model. Nothing happens. Nothing happens differently because there is no containment measure. So this is the SI model in unified population. The number of infected individuals increasing time exponentially fast, and the epidemic threshold individual. So any epidemics in this model, it leads to a pandemic, to an outbreak. So what is the effect of temporal kernel in these dynamics? Can decay modulation of the infectivity f of tau induce an epidemic threshold? What is the expected time evolution of the number of new infected individuals? Would the exponential onset of the epidemic be affected by the temporal kernel? So in the case of a rather slow decay of f of tau, we obtain that the epidemic threshold remains equal to 0 if alpha is less than 1, if a power law exponent alpha is less than 1. This means that the containment measure is not fast enough to stop, halt the epidemics. If instead this exponent is greater than 1, the containment measures are able to contain all the viruses spreading with an infectivity smaller than the critical value. So they are successful, but actually we notice that this infectivity is bounded. So if the virus has an infectivity which is above this bound, it cannot be altered by a containment measure which leads to a detection of case which is just decaying as a power law in time. So this scenario is more rosy if the temporal kernel decays exponentially or with a generalized exponential. And in this case, the chosen parallelism of generalized exponential can induce an epidemic threshold and therefore halt the epidemic if they are chosen correctly, in the way that there are a set of parameters gamma and beta that can stop the epidemic. So the first message of this work is that if the containment measure does not result in a fast enough reduction of the infectivity of the infected individual, the containment is not enough to halt the epidemic spreading and has only mitigating effect. We then look at the total number of infected individuals, and we saw that in the supercritical phase for lambda greater than lambda c, this number is always increasing exponentially. For lambda less than lambda c is always equal to a constant, but at the critical point, it increases linearly or sublinearly. Then at the time in which we were preparing this work, the disease was rapidly spreading in different countries. The number of countries in which at least one COVID-19 death, if you see at least one COVID-19 death, follows this curve that you see in the picture. And so there is a plateau, there is a plateau due to the fact that several countries, including China and South Korea, had in place very strong containment measures. But then at the time we were writing this work, the number of countries affected by the disease increased steeply, leading to the WHO, to the fact that leading the WHO to declare a pandemic. So when we consider a multi-foci model when rho of t determines the number of new foci establishing at time t. And again, we adopt a toy model approach, mean field approach. So we assume that all the foci have a similar dynamics and that the total number of impacted individuals across multiple foci is given by this expression. It's just the sum of all the infected individual in each country, but every country has its own delay because the start of the epidemics start at different time. So in this model, we find that in the supercritical regime, again, we find this ubiquitous exponential, but in the critical regime, we can find a power loss. And so this leads to the second message of this work, that at the onset of the epidemics, the new infected individual will grow always exponentially in the supercritical regime. But if we are in the critical regime, they can grow as a power law. So in light of this work, the result of ZIF and ZIF can be interpreted as the result of a multi-foci dynamics at the critical state. And this interpretation is in line with the fact that China is a big country, so it must have many foci of the epidemics. And there is evidence that we were at the critical point because the disease has been altered in China. So I want now to discuss briefly what is the role of stochastic process of how can we describe the SIR model beyond its deterministic solution. So the stochastic model that we know to treat and solve exactly is the branching model that constitutes an evergreen model. And this is the stochastic model of the SI model in infinite population. So every infected individual at time t causes the presence of 0, 1, 2, or in general Z infected individual at time t plus 1, with an average given by R0, so the reproduction number, and we assume for simplicity that we have a finite second moment. So in this case, the avalanches spread at infinity if R0 is greater, if and only if R0 is greater than 1. And the critical dynamics is obtained for R0 equal to 1. This dynamics is strongly affected by fluctuation as shown by the statistical property of the outbreak size and the duration of the outbreak. So indeed, this model also captures the property of the SIR critical dynamics. And we have that the distribution of the size of the outbreak of the critical dynamics follow a power law with an exponent 3/2. And so indicating that also the average is strongly affected by the cutoff and ultimately the population size. And we have also a distribution of the duration of the critical outbreak, which is also widely distributed. This means that there are very large fluctuations of the duration of the outbreak and in this critical regime. And the work by Ben Naim and Krapinski clearly established the relation between the cutoff of this distribution and the population size. So assume that you have a city of 1 million individuals, so you are in a critical state, so you are at the peak where the R0 is equal to 1, so you, and if you start from a single individual, then the the expected outbreak size will be 100 individuals. But the second moment will be 1,000. This means that you have a lot of uncertainty in your prediction, and the same for the duration of the outbreak. So here I come and comment on the question of the plateau duration. So we know that the plateau is characterized by being a critical state induced by containment measures. Fortunately, not by herd immunity as the SIR peak. So in this phase, we should expect that the dynamics is strongly affected by stochastic event and fluctuation. And therefore, I suspect that in many countries, we will face this challenge to estimate and predict this plateau, which will be quite elusive because of this stochastic phenomenon. Let me now finally discuss about the network effects that are so close to our interest and passion. So the stationary property of the SIR model are dictated by link percolation. So you assume that every link transmits the disease with a probability given by a parameter, which is called transmissibility, and that by following the links, the activated links, it is easy to show that the final outbreaks will be given by the connected component of the affected individual, like this red component in this picture. So if this component is giant, so it's affecting a finite fraction of the population of the network and the population, we are above the percolation threshold. And from this percolation threshold, which determines the moment at which we have the emergence of this giant component, we can also easily find the epidemic threshold. So by using the expression for the percolation threshold, we obtain that in a network R naught on an uncorrelated network with given degree distribution is given by the transmissibility and this other factor here, which is called the branching ratio, which depends on the topology, in particular the degree distribution of the network. And this expression has very profound consequence for epidemic spreading in a network. First of all, this branching ratio diverges for scale-free networks, for networks with very broad degree distribution. So scale-free networks are very prone to sustained pandemics. So the epidemic threshold is effectively 0 on scale-free graph, and hubs are more likely to be infected. And we have also positive side of it, that targeted immunization of the hubs can be very efficient. And this has been very nicely discussed in previous talk. So if we focus on network effect, of course, one of the most important things we can look at is the fact of social distances. So social distancing measure will change our not by changing, for instance, the degree distribution of the network. So by removing the fact of big hubs, but it can also just sparsify and localize the disease in one region of the network, as very nicely shown by this visualization by Nicola Perra. And this localization of the epidemics and this sparsification of the network can lead to the very desired feature that this curve is flattened. But under the pressure to define exit strategy for containment measure, a network scientist can be tempted by considering optimal design principle. So thinking about increasing the density and decreasing as much as and increasing as much as possible the epidemic threshold. And this comes with a risk. So the current understanding of these problems show that the optimization could come at a significant risk of having an explosive and therefore uncontrolled transition. And so this is what happens, for instance, in explosive percolation or in approach of large deviation to percolation, where you are successful in pushing the epidemic spreading, the epidemic threshold, to increase the epidemic threshold, but this comes at a cost that at that point you have a sudden increase of number of infected. So any prediction in predicting when a big jump might take place will lead to a catastrophic abrupt increase in number of cases. So one needs to be a little bit careful. So here, as promised, I want to mention then now the effect of generalized network structure on epidemic spreading. And these include multi-layer networks, simplicial complex, and temporal networks. So thinking about life under lockdown, as has been my life for some time now, I believe that multi-layer network and modular structure of the society is a very important factor to take into account. And then also one needs to consider epidemic spreading on simplicial complex and network with clustering or very densely connected and large clique. And then you have, of course, the important effect of time, of temporal networks. So multi-layer networks are networks in which the interaction can have different character and different implication for dynamical processes. This structure are discussed in great detail in my book, Multi-Layer Network by Oxford University Press. Most of the results so far have been focusing on multiplex networks, which are very interesting. But today I want to speak about a more general multi-layer network structure in which every layer can be understood as a community and each node has a certain degree within its community and across different communities. So here, so for instance, node I has a certain degree in layer alpha and a certain number of links in each of the other layers. So in this situation, you can consider the fact of degree correlation. So, and you can see that there are an anti-correlation of the multi-layer degree can lead to a more resilient multi-layer network. So in an anti-correlated degree means that the hubs that are more connected across different layers should be peripheral in their own layer. And instead, if you have positive correlation, of course, this is favoring the spread of the epidemics. So in what you really like is a scenario which is here drawn schematically, in which the nodes that connect different layers are the peripheral one. And this can be really mathematically formalized. So the degree correlation between the degree of the node in its own layer and across different layers can help modulate the epidemic threshold. Other modular networks are very important, like hierarchical network already cited in other paper, or modular network like the Lancichionecchi-Fortunato-Radicchi model. And there are these two interesting papers by Morelli et al. And Odor et al. That study epidemic spreading in this highly modular structure. And what I found very interesting is that the scenario is a bit different from the one I've been talking about since now, because there are two epidemic thresholds separating an extensive region of critical, region on one side from the subcritical phase and on the other side from the supercritical region. So these results are obtained in the framework of the SIS model and show that this particular topology are such that they can be highly affected by strong fluctuation for a wide range of the infectivity value. So this phenomenon has been related to Griffith phase and to rare region localization of the disease. And the evidence for this scenario is for the mostly numerical. So now let's discuss about simplicial complexes that are raising very significant interest recently in network science. So these are objects related to hypergraph, which are formed not only by nodes and links, but also by more dense cliques such as triangle, tetrahedra, and so on. And simplicial complex can result, for instance, in a simple model of triadic closure, generating spontaneous emergence of community. Interesting, in a very simple example of simplicial complex, we found a similar behavior observed in modular hierarchical networks, and we found two epidemic thresholds in which, such that in the extensive critical region, let's call it, we have a number of recovered individuals which increase with the population size sublinearly. So it's like a critical region. And then we have a region in which we have an extensive size of the infected individual. So in this context, the presence of the two epidemic threshold is solidly based on analytical and numerical approach. And this provides an evidence that the occurrence of these two epidemic threshold and this wide region of criticality is actually not so rare as can be initially thought. Finally, I also want to signal to you a very interesting paper of Laurent put on the archive last week, where he and his collaborator explored the very interesting model of epidemic spreading in simplicial and higher order network, finding again this phenomenon of localization of the disease, which is related to the phenomenon discussed previously. I want to conclude this talk by telling you about the effect of time and temporal network and the effect of temporal network in epidemic spreading. So in face-to-face interaction, there is evidence that the interactions are busty, meaning that the duration of an interaction is described by a power law. So it's can have very large fluctuation. And this is an effect that is observed not so only at the level of pairwise interaction, but also at the level of temporal simplicial complexes. So the temporal meeting of 3 or 4 people have a duration which is again decaying in time with the power law, and the power law is steeper and steeper the larger is the network size. And these are real data coming from one of the Socio-Pattern experiment, and some of this data can be aggregated, forming aggregated network on simplicial complex like this one, very beautiful one from the Socio-Pattern data of measured in a museum setting. And actually we can relate this feature, the busty nature of the interaction of temporal network, to old observation by Pastor Satorra and Bestignani in the early days of their modeling in epidemic spread in 2001. So they noticed that the antivirus for this computer virus that we're studying, so despite the antivirus for this virus that we're studying are ready within short time from the release of the virus is long-lived. So the virus have a long time in the network. And a paper, this paper called Small but Slow World, show that actually this might be an effect of the busty nature of the interaction that are driving the dynamics both online and offline, as we have seen. So this clearly sends us a real warning, possible warning about the possible the duration of the current pandemics, but of course, we believe that a vaccine will be widely diffused, but the challenge is that that these these pandemics can be very long-lived. So with this consideration, I conclude my presentation. I want to thank all my collaborators, and in particular, the co-author of the work that I discuss, and first of all, Paul Krapisky from Boston University, with whom I collaborated in this recent work on containment measure that I told you about. And I want to mention also scientists with whom I have collaborated or I'm collaborating now, and these include Bob Ziff, Filippo Radicchi, Santo Fortunato, and Alain Barra. So before I conclude, I want just to say that it's very difficult to make prediction, but one prediction can be made at the time of COVID-19. And this is that the scientists will be busy understanding this pandemic and its impact in nature, economy, and society for years. And I believe that there is much need of data-driven prediction, but also at the theoretical level, there are gaps in our understanding of the possible dynamics that can be explored by this virus. And there are many questions that need to be asked and answered. And I believe that the mathematical and theoretical understanding should go end-to-end with data-driven approach. And there is yet a lot to do. So I wish for us all good work and stay safe, and well, thank you for your listening.
Thank you so much, Ginestra, for that excellent presentation. Applause, virtual applause, real applause. While we're getting some more questions in the chat window, let me start us off here. So you presented some simple, elegant modeling for modeling epidemic spread, and then you went over some nice higher order network effects that we can think about, like multi-layer networks, temporal networks, simplicial complexes. So can you give us a sense of what your expectation is if you wanted to capture, to better model the spread of COVID-19? How would you order those higher order effects in terms of what would you do first? What do you expect will have the most impact in creating better models?
Yeah, I believe that simplicial complex will be clearly very important, because this lockdown, you know, it's really imposing a structure in the society which is very modular, or, you know, with large cliques also. So the households are clearly cliques, and but you know, more widely, you know, if you go behind household, of course, I think that there will be a more sparse structure, like more modular structure. So maybe some simplicial complex that includes some randomness in it, so that there are not only triangle and tetrahedral perfect structure, but this is blended with random links and things like that. And of course, I think that all this work make me think a lot. And I think one of the pressing challenge now, if I see from people coming from Italy and things like that, is really to understand how long this will last at such level. So if the containment level measure are effective in, you know, in stopping the increase of the cases, the increase of the steep of this curve of that. So and reach an R0 equal to 0, if R not equal to 1, then how long should you wait for this peak to fade down? This is something that really is my question now that I want to ask.
Great. And there's another good question that has come up about the stochastic side of things. So asking, it seems like you're calculating the full probability distribution of outbreak sizes from a stochastic model. And this probability distribution reflects how stochastic effects enter into the model. But if you're working with real world data, you get one instance of this, and or a few very small instances. So is there a way of verifying that the stochastic effects in the model are appropriate for the real world epidemics?
Yeah, I think I will turn this question around. I mean, yes, it's the stochastic effects are surely there. The problem is, are they so significant? I mean, in the critical regime, we know that they are so significant. So prediction is a risk to be quite off if you are in the critical regime. But of course, we might not be in the critical regime, and this I don't know if it's good news or bad news, because if we are in the supercritical regime, of course, it's very bad news because the epidemic is spreading very fast. And our goal is to go through the RZ R naught equal to 1 and pass through that and go in the subcritical regime. But how fast can we do that? Because with herd immunity, you have this peak of the SIR model, which is fading very fast, because the probability that an individual, the R naught is lambda S, lambda number fraction of susceptible individual. So, and if you start for a very large lambda, okay, you start with a very large lambda, you reach the peak, so the susceptible individual decrease, and you are reach 1. And then for any new people that is recovered, R0 is lowered because S decrease. So you have an automatic, in the SIR model with herd immunity, you have an automatic way to escape this critical regime. But with containment measure, you don't, because you don't have herd immunity, fortunately. But then you are really in these thin ice, as Angela Merkel put it, that you are there and you need to be careful of this fluctuation. If it's 1.1 or 0.9, that you prefer much better. And this is exactly the problem, I think, that many countries that are ahead in the evolution of the disease, like Italy, but also like UK, are facing. So this decay is not very fast. And why is that? So it can be an artifact of the data. Many people think also about that. Delay in the number of counting of people. But we cannot trust the mechanics of the SIR model, which leads to a peak that suddenly goes down.
Thank you. That's a lot to think about. And, you know, some of it is very hopeful in terms of giving us a path forward to model better. And some of it is obviously quite a warning. But thank you again for a fabulous talk.